Hey guys, welcome back to Food for Thought, where today we're going to be continuing our discussion of physics. So last time what we did was we set up a reference frame and a coordinate system to do physics on. And what this is right now is just a straight line with positive values on the right and negative values on the left. So now we have a coordinate system set up, it's time to start putting objects into this coordinate system to do physics with. Now any object in this coordinate system is going to have a position, which we're going to represent with the letter x. So a position just tells us where in the coordinate system this object is. Now it is important to note that position is a vector value, which if you remember, a vector is going to be any value that has both a magnitude and a direction. What this means for us right now is that the position can either be positive or to the right of the origin, or negative, which means to the left of the origin. Now in most physics problems, your objects aren't going to stay still. Their positions will not be constant. They're going to move around over time, and the position is going to change. So we can represent this by graphing, say, by making a function of position against time t, because the position might change over time. So we can graph this with position on the y-axis and time on the x-axis. So for instance, one example of a position function might look like this. So what we see here is that the position of this object, well, it starts on the positive side, because over here we're going to say is positive and down here is negative. So it starts positive, it goes a little further right, comes left a little, goes back right, goes left a lot until it goes into the negatives, and then comes back right until it ends up somewhere here in the positives. When objects move, they move with a velocity, which we're going to represent with the letter v. And the definition of velocity is that this velocity is going to be the derivative of position with respect to time. Now this word derivative is very important, and it is actually a calculus concept. So a derivative is going to mean the instantaneous rate of change. It is a calculus concept. If you don't know calculus, it's fine. You don't need to here. This is a physics course, not a math course. So we don't need to really know all the math behind how to compute derivatives and stuff. However, it is important to understand what a derivative is. So as I said, a derivative is an instantaneous rate of change. So for instance, this v over here we're going to write as equaling dx over dt. And this is standard notation for a derivative. It stands for the derivative of x with respect to time. And what this just means is, well, the velocity at any one given point is just how fast the position is changing at that point in time. So we can visualize this like this. So let's say we have an object moving along with this this function over here. Right, and let's say we connect this starting point here with the ending point over here. Then we have this secant line over here, and the slope of this line is and we're going to call this line v bar. This bar here stands for average, so this is going to mean average velocity, and we're going to write v bar equals, well, we're going to the average velocity is going to be the slope of this line, and slope, as we know, is rise over run. So we see the rise, or it's negative here, I guess, but it's still a rise. We can see, well, we started at this x over here and ended at whatever this x is over here. So it's this change in x that we're going to call delta x, delta position, and then we're going to divide that over the change in time, which is delta t, or change in time. And this this slope of this line here, this delta x over delta t is going to be our average velocity at any given point. Okay, well that's all good and all, but let's say we want to find the velocity at any given point. Say the velocity over here, at this exact moment in time right here. So if we want to do that, what might we do? Well, we can think of it like this. We can take more average velocities, but slowly shrink the intervals from which we take them. So for instance, we can take one from here to here, from here to here, from here to here. And the idea is if we keep getting closer and closer to this one point that we want the instantaneous velocity at, eventually what we're going to get is just a line that is perfectly tangent to this curve at that one point. And we put this in red. The slope of this line here, which is the slope of the line tangent to the function at that one point, is going to be the derivative at that point. The instantaneous velocity at that point is just the slope of this line. And that's what we're going to write as dx over dt. This velocity right here. So this is an important concept. The derivative is simply the slope of the function that has x over t right here. So our velocity is dx over dt. That means the derivative is just going to be the slope of the function of the tangent line to the function at that one given point. So that's an important concept. Now another important thing to note is that velocity here it's also a vector. Just like position, it can be either positive or negative. Now this velocity here is different from speed. So this is not going to equal speed. Speed is a more commonly used word that means something different in physics context than velocity. So speed is actually going to be a scalar. It only has a magnitude. Speed just tells us how fast we're moving, while this velocity here is going to tell us in what direction we're moving as well. So for instance, if our speed is just going to equal, say, speed equals average speed for now, let's say, equals delta of distance over delta time. And what this means is just, well, speed is going to be our change in distance, or rather total distance covered. The delta is not really appropriate, I suppose, but the speed is just going to be the total distance traveled over the change in time. And this is different from here, because here we see this is just a change in position. So here we can see we moved around a lot, but ultimately our change in position was not very much. This line is almost horizontal, because our ending point was very close to where our starting point was actually. So here our speed might have been big, who knows, especially here when this slope is big. But our average velocity is actually very small, because in this amount of time, even though we moved around a lot, we have only covered a small amount of distance. So our velocity is going to be very small in the negative direction. Okay, so that's important to understand. Velocity is a vector, while speed is a scalar and somewhat less important and such. So now what we're going to do is we're going to re-express this expression right here, which is very important. This velocity equals dx over dt. We're going to rewrite this as x. We're going to solve this for x, and we're going to say x is the integral of velocity with respect to time. Now this integral here is also very important. An integral is the opposite of a derivative, I suppose. It reverses the process of a derivative. While your derivative here is going to tell you the rate of change, the integral tells us how much change has occurred. So for instance, let's just plot velocity with respect to time over here. Going to plot a random velocity curve, say something like that. This is different from this curve over here. So with this velocity here, we can see, well, we start out moving in the positive direction at a positive velocity, get a little faster, slow down a little, get faster more, slow down, but we're always remaining in the positives. Okay, cool. So this is not going to be the velocity of this particle right here, which should be not fairly evident. But basically, let's say we want to find the total distance that we've traveled between 2 points, say here and here. And I'm going to label these times as t0 and t1. So we want to find how much distance have we covered moving at whatever velocity function this is, from t0 to t1. Well, the integral is just going to be the area under the curve here. So for instance, if we somehow add up all this area over here, we can find the total distance that we've covered in this amount of time. Oops. So now, in calculus, there are ways that we can use to calculate the exact derivative and integrals of various functions. But this is a physics course, so we're not going to be going too deep into the math there. It's simply important to understand that the derivative is the slope, and the integral is just going to be the area under the curve, from the curve all the way down to the x-axis. Now, one important thing to note, let's say that we have some other velocity function that dives into negatives over here, like that. Then when we take this area here, that means that we're actually, since we can see here in velocity that we're moving in the negative direction over here, so if we take the area over here, that's negative, that means we're actually going to be moving left. So our net change might be going left in this period of time at least. So yeah, the integral is going to be the change in position. So now one more thing we're going to define. When objects move, their velocities are usually not constant. For instance, they're usually going to have an acceleration too. So acceleration we're going to define as, with the letter A, is going to equal dv over dt, or the change in velocity, the derivative of velocity with respect to time, which is just going to be the slope of the velocity curve. And similarly, we can write also that v is the integral of acceleration with respect to time. So the area under the acceleration curve is going to be how much our v has changed in some given amount of time. So usually, again, as I said before, we're not going to go too deep into the math here. There are ways to calculate derivatives and integrals. They're not going to be too important right now. However, there are two special cases of movement that we are going to cover, and we are going to take the exact derivatives and integrals for. Those are going to be constant acceleration and constant velocity. And those cases are fairly simple. We can actually compute the exact derivatives and integrals using these definitions of area and slope. And knowing those equations is going to help a lot in many of your kinematics problems in the future.